Hello and welcome to seminar number 25. Today we are going to talk about nuclear reactions. So I will give you some basics about the nuclear reactions so that you know a bit about nuclear chemistry. But the actual trigger event for me making this presentation was a patron of mine asking me, hey, I have this really weird sample that Luciteria sells. Is this legit? And I just wanted to give you some fundamental knowledge about nuclear reactions so that we can all be on the same level when it comes to, I have no idea what Luciteria actually sells there. So, starting with a bit of nuclear chemistry history. First of all, nuclear chemistry began when Henri Becquerel discovered that uranium was radioactive or was radiating away some sort of radiation that was of sufficient energy to develop a photographic film. Then, 3 years later, Rutherford actually looked at it and said, well, it's just not one uniform type of radiation, but coming out of uranium, we have 3 different types of radiation. I don't know if you differentiate actually between 3, but he said there were different types of radiation. Interestingly enough, after 9 years, he was able to identify one of these types of radiation to be alpha radiation, which was made up of helium nuclides. And this whole nuclear chemistry history part is really interesting if you look back at it, because the discovery of polonium and radium, which we know as very prominent alpha emitters, was published way earlier than this. So they had this really interesting, which we now call just pure alpha emitters, but they didn't know what the radiation was that they were giving off. So it was just radiation, which is really interesting. And even more interesting is it if you look at the publication date of the atomic nucleus, which was 11 years after the discovery of polonium and radium. We now identify new elements by having a new nucleus with one additional proton. And we know that ionizing radiation comes from the nucleus. But back then they had this raisin bread model by Thomson, and they first of all isolated these highly radioactive new elements, which are described by the proton number inside of the nucleus, but they didn't have a nucleus, and the radiation came out of the nucleus, which again, they did not know what this radiation was made up of. And additionally, they didn't know where it came from because there was no nucleus, because we only had the raisin bread model. So it's really interesting bit of history. So coming back to the actual topic of today's presentation, it's the nuclear reaction. And the first classical nuclear reaction was described by Rutherford in 1990. And this was the nitrogen alpha p oxygen 17 reaction. The alpha particle in this case came from natural radiation. It was the polonium-214, which is really short-lived, most likely just produced from bismuth or lead-14 sample. And according to the Geiger-Nutter rule, the shorter lived a alpha emitter is, the higher its energy. So the alpha particles of polonium-214 were of sufficient energy to induce a nuclear reaction on atmospheric nitrogen-14. And first of all, he just wanted to study the scintillation of his zinc sulfide film there. But interestingly enough, he then put a piece of paper between the alpha emitter and the scintillation film and noticed that the scintillation persisted, which is interesting because the blockage of the alpha particle was so thick that no alpha particles could induce scintillation in the zinc sulfide film. So he then proposed, we now have, because of some sort of reaction, some more long-ranged particle radiation that could then again induce the scintillation of zinc sulfide, which, I don't know, maybe copper doped. And these were protons, and he published the first classical nuclear reaction, which in a cloud chamber looks something like this. And if you ever find a YouTube video where you can see this nuclear reaction happening inside of a cloud chamber, please let me know. I really wanted to see that in a cloud chamber. Knowing me, I will not find the time to do that myself. But yeah, you need alpha particles of enough energy. And I will come back to that on the later slides when it comes to more basics. So we have this nuclear reaction, and we in nuclear chemistry describe nuclear reactions with different terminology. So in red, we have the target. It's the base material that gets irradiated. in this case with alpha particles. Alpha particles are the projectiles. Depending on their energy, you could achieve different types of nuclear reactions. This is the incoming particle, but you also have another outcoming particle. Sometimes it can be a photon, for example, the N-gamma reaction. And in this case, it's a proton. We call this proton, in this case, the ejectile. Most of the time, it's just any particle that we do not further care about because we wanted to produce the residue, which is most of the time the radionuclide that you actually wanted to produce. In this case, it's oxygen-17. No one uses oxygen-17, in my opinion. But most of the time, you wanted to make the residue. For example, oxygen-18, PN reaction fluorine-18. The residue is the fluorine-18, and this is the radionuclide that you wanted to produce for your pet chemicals, for example. Going even further, when we are talking about the alpha particles, for example, or protons, we are talking about positively charged projectiles. And these acquire accelerators, because you can't accelerate something neutral, like neutrons. You will then have the just reactor or the neutron source in case. But if you are accelerating positively charged projectiles onto a nucleus, which is also, that we now know, positively charged, you will need to account for Coulomb repulsions because your particle beam and your target material could encounter Coulomb trajectories. To describe how well this nuclear reaction works, we know this from chemical reactions. We know that we have some sort of term, which is the K value, indicating how well this chemical reaction works. In our case, it's the cross-section. The unit is called barn, and 1 barn is defined as 10 to the power of minus 24 square centimeters. So it's the cross-section of the nucleus that the particle sees when encountering this nucleus. So, for example, it's a neat coincidence. If you look at uranium-235, the actual nucleus itself, if you do not have 3 division, but only 2 division, the section, like the circle area of this nucleus, the area, this is 1 barn. In this case, it's the geometrical barn. So it's actually the cross-section area of this nucleus. But in some cases for nuclear reactions, the nucleus can appear larger. And this is then, for example, like 2 barns for the, N neutron scattering reaction. Also, depending on the energy of the incoming projectile, we differentiate between direct nuclear reactions, which mostly involve fast projectiles and can happen on the surface of the nucleus. It's like flinching a stone over a surface of water. And these nuclear reactions are occurring very fast. It's in the order of 10 to the power of minus 22 seconds. But, for example, the fluorine-18 production, which I talked about in the previous slide, is a compound reaction. So we actually have, when the oxygen-18 nucleus encounters the proton projectile, they will form a fluorine-19 compound nucleus, which is then stable for orders of magnitudes in the 10 to the power of minus 16 seconds and can then decay, emitting a neutron, leaving behind the residue, which is in this case the fluorine-18. Now we have all of the scientific stuff around nuclear reactions. We can now look at nuclear reactions, and these are screenshots from the Janus website. In this case, we have uranium-235 and fission, so thermal neutron-induced, neutron-induced fission. On the y-axis, we have the cross-section, so how well this nuclear reaction works, and on the x-axis, we have the incoming neutron energy, so it's microelectron volts up to gigaelectron volts. And this is the cross-section, and for example, we have an energy range, in the case for neutrons, we call these neutrons cold neutrons. And if we look, a cold neutron with 1 millielectron volt of energy is really good at inducing nuclear fission in uranium-238. But we don't use it because we have thermal neutrons, and to produce thermal neutrons, it's just a matter of letting paraffin or water do its thing. So we do not have to cool the moderator down in order to produce extra cold neutrons, which would, in our case, mean just additional effort to put into. It's okay. Thermal neutrons have a really high cross-section. It's around the, 200, 300 barn cross-section, which is really good. Of course, colder neutrons would be better when inducing nuclear fission, but having neutrons of even less energy than 25 millielectron volts, which would mean additional effort. anything above that, we see this really funny error here. These are the resonances. So in some energy cases, so in different energy ranges, you have different resonances of the nucleus. And if a neutron by chance could hit perfectly this resonance of the nucleus, it could induce fission very well. But on the other hand, if it's just a slightly bit off, the cross-section goes down to 0. So it's really a pain in the butt if you want to do neutron-induced fission and relying on these resonance neutrons, because you can't precisely make neutrons of this or that energy. It's really hard. Well, you can, but it's just too much effort to do. And anything above 1 mega electron volt, you have the fast neutrons. And as you can see here, the cross-section, it's okay-ish, but it's just way worse than having thermal neutrons. All right, I wanted to show you again another nuclear reaction. In this case, it's the N-gamma reaction of uranium-238, leading in the end to the production of weapon-grade plutonium. And you can see here we have the resonance area in this case, and we have the thermal neutron range here. As you can see, it works quite well. And with the fast neutrons, it also works not much worse. Don't store uranium and aluminium because you might be able to accidentally create neutrons. This is a saying from Radioactive Drew on YouTube. I don't watch his YouTube videos. I get sent some of his videos by some friends of mine. And maybe he has now corrected his statement. But I remember that he said that in one video, that you should not store your alpha emitters, in this case, for example, uranium, in aluminium because you could create neutrons. If you look at the nuclear reactions that could produce as a ejectile our neutrons, it's the aluminium-27 alpha N reaction producing phosphorus 13. You look here, we have a certain energy maximum for our nuclear reaction, and this is depending on the incoming energy of the projectile. In our case, it's the alpha particle. And if you look at the typical alpha emitter that one might have at home, it's americium-241 with this alpha energy around about here. And if you look at the cross-section, is around 20 millibarn at most. If you look at the highest energy alpha emitters that one might have, which is polonium-214, which is part of the naturally occurring uranium-radium decay chain, which has a alpha energy of 7.6-ish mega electron volts. You can look here, we have a cross-section of 0.1 bar. Okay, is that much? Well, if we look at the actual nuclear reaction for producing neutrons, in our case, it's the beryllium-americium source. You look at the alpha-induced nuclear reaction, and if you look, in our case, we have a neutron source with 65 gigabecquerels of americium-241. The alpha energy lies here in the maximum for this reaction, and we have a cross-section of 0.2 bar. Is that much? Not really. Very common nuclear reactions, we say that anything with a cross-section of 1 bar or above is a really well-occurring nuclear reaction. But in our case, we need 65 gigabecquerels of americium, something that no normal person has at their home. And with this scarily huge amount of americium-241, we can only produce 1 million neutrons per second. And in any given irradiation place that we have, we get about 300 neutrons per second, which is coming back to your average radiation enthusiast. I don't think they have 65 gigabecquerels of any alpha emitters. And I would just say, just ignore that. However, I wanted to give him the benefit of the doubt where he might have heard that, because this information was part of the Manhattan Project, because they wanted to make a plutonium bomb. And the difficult part is when making bombs is that you have your fissile material. In our case, it's the plutonium-239. And you wanted to make it as smooth of a bowl as somehow possible. Because if you then crush it down to induce criticality and stuff like that, you need a very smooth surface in order for the compression to be very evenly distributed and not just deforming your bowl of very precious material, just melting it down and not making this explosion. So they were trying to make some sort of alloy because plutonium is very dense, and making this plutonium ball very smooth was very hard. So they were like, hey, how about we just use an alloy that we can then hammer down to make a smooth surface and then have our ball. And they were also experimenting with a plutonium aluminium alloy, which might work, but when encountering some tens-ish kilograms of plutonium-239, this reaction actually does something, and they had the fear that this alpha-induced reaction for the plutonium could induce fission too early, leading to also just a failed bomb material. So they scrapped that idea, but this is where this information came from, that aluminium-27 can produce neutrons, which is true, but this was only a concern when having some kilograms of weapon-grade plutonium. It's not something that would apply to most of you. Yes, it might be, but I don't think you would actually be able to measure it, even if you were to store some kilograms of pitch blende in your tinfoil, which is made from aluminium, right? So aluminium is good at shielding beta particles, and this nuclear reaction should nothing be of a concern for the average nuclear chemistry enthusiast, right? Get a bit of the context where this information comes from. So it comes from the Manhattan Project and them trying to make a smooth plutonium-239 ball. It's really interesting knowledge, but a bit out of context in this case. Luciteria. So, if you look at the text, there's some very true statements in there, but also they do not just match with the hinted nuclear reaction that might produce you your interesting radionuclide. So first of all, if you look at the text, you can see that they are talking about curium-242, which is really interesting. And then they go on to talk about the death of curium is a violent British event, blah, 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 supernova, and the ejector produced, in our case, it's the alpha particles, they might, atom of helium, they might encounter another curium atom. And if that, someone has to be a sister of curium, kick up a notch to form berkelium, number 90. You have to look at the chart of nuclides, which also made several videos about how to read it. And if you look at curium-242, so we're starting apparently here, alpha-induced reaction means for us that the highest possible element is just an alpha-gamma reaction producing the californium-246. Alpha-gamma reactions are very uncommon, so might be a alpha-N reaction or alpha-2N reaction or a alpha-P reaction, for example. In our case, forming maybe the berkelium. However, I was trying my best to find some data for this maybe occurring nuclear reaction, and the only thing which isn't added to the presentation which I gave on the Red Zone 2 Discord server. I held that seminar before, and this is one again just for YouTube, and I have to correct myself because then I said there were no available data for alpha-induced curium-242 reaction, but my professor looked at it and is like, no, there is one. This is the alpha-N reaction forming californium-252, which was done in the 1950s. It's very uncommon, and there are no cross-section for this nuclear reaction. So it's a really uncommon nuclear reaction which, again, produces californium. And yeah, okay, californium might be able to decay back to berkelium. It's really dodgy, and it's really niche application, which I would not want to rely on. Also, if you're talking about berkelium, which again, yeah, berkelium has this isotope, the 249, which is really interesting. But looking at our apparently starting material, curium-242, how do we get there? We want to get here because they are talking about the berkelium-249. And again, berkelium-249, which is the most important radionuclide of berkelium. But it's not something that you might be able to produce from curium-242 if you are actually starting with curium-242, because otherwise, I don't see a point in mentioning this in this paragraph here. Like, yes, it decays by alpha decay. Yes, the alpha particles are very fast, and maybe they could induce this nuclear reaction, but not in this sample. Alright? And again, they are not producing the berkelium-249, which you go on to talk about in the next parts of the paragraph. So then I was looking a bit further, and I saw the curium element sample, and they actually gave us some data, and they are going to talk about actual quantities of curium. So it's the curium-242, 243, and curium-244, which again, 0.7 picocuries is not that much in terms of having an element to do nuclear reactions on. But it's again very impressive that they actually have some sort of proof that they have these isotopes in there. So we have confirmed that we have these 3 isotopes. But to be honest, if you're selling this cube for 3,000 euros, a thermino spectrum of the gamma lines is not the state-of-the-art proof of existence for curium. You might be able to just email some sort of nuclear lab and run it through a high purity germanium detector and not rely on some hobbyist thermino spectrum, in my opinion. It's a good one for hobby or enthusiasts in the private sector, but for a company, I think you could do better in that case. Then I was scrolling a bit further and I saw the Californium sample, and again, it's just not making sense. So yeah, curium is the gift that keeps on giving. Yeah, breaks up, might be producing a small quantity of berkelium-249, which turn will decay into californium-249. So the only curium isotope that is able to produce berkelium via its normal decay and not just some absurd nuclear reaction is the curium-249. So here, and then decays here, and this decays into californium. So yeah, curium is really an interesting radionuclide. But looking at the half-life in 64 minutes, that's not something you can store. Maybe you can deposit onto it, but no, you can't deposit onto here because you do these types of reactions in a really high flux nuclear reactor. And once you get it out of it and be able to purify all of this, this will long be decayed into berkelium-242. So you can't really deposit curium-249 onto something which would then decay because it decays via the isolation process and you just start with already decayed up berkelium-249. Unfortunate. So, first statement, berkelium from alpha-induced reaction on curium. Again, if you look at the Genesis website, you won't be able to find any data for alpha-induced curium-242 isotopes. We were able to confirm that there are some nuclear reactions, but of course they are poorly described and not something I would rely on for a element sample. I was able to find on the Genesis website alpha 3N reaction for curium-242, which we have confirmed is in the hands from Luciteria. They stated that they have curium-242, 43, and 44. But if you look at the data, which is here the calculated one, and this is the experimental data that we have, this nuclear reaction starts at above 25 mega electron volts, which is not the alpha energy of any curium isotopes. They have alpha energies in the range of maybe 7 mega electron volts at most. You won't be able to induce this reaction because there is just not enough excitational energy for these nuclear reactions to occur. However, berkelium from curium is technically possible. They stated that. But it's just not possible with the curium-244, 43 or 42 isotope. It's only possible for curium-248, which would then be bred into curium-249, which can then decay upwards. But just to give you some context, it requires a really high and constant neutron flux. At Oak Ridge, they need about 3 months to breed anything past curium from their curium aluminium oxide target, and they use highly enriched uranium for this neutron flux. And also I just wanted to mention that no protons or deuteron induced reaction. Even though they might be described in the literature, we don't have any protons or deuterons available. Alphas do not have enough energy, as we saw in the previous slide, and as I said, constant neutron flux. Maybe we can breed our curium-249 from our isotopes that might be present in the in situ somehow. Spontaneous fission, right? Fission produces secondary neutrons, but if you look at the fission proportion of these isotopes, it's just neglectable. If these were to do fission, they would produce fast neutrons, and most of the capture reactions happens with thermalized neutrons. So you have to thermalize them, which can't be happening on some sort of iron plate that they have it deposited on. So it's just not possible. and breeding from curium-244 up to curium-249, which is 0.7 picocuries, it's just really unrealistic because you would have the same neutron hitting the same atom more than twice. Need 7 neutrons hitting the same atoms. For this to be statistically somehow feasible, you need very large quantities of curium-244, and this is not something given here when starting with 0.7 picocuries of curium-244. And then I just wanted, so now we know that this is all it's just true statements in the text. However, these true statements do not apply to what's indicated on the content of the element sample. And yesterday I stumbled upon the Reddit post where someone was mentioning Einsteinium. See for yourself, we have a smidge of curium. Okay. We now know that there is a huge difference in which curium isotope you actually have. Because scientifically speaking, there's a big difference in having curium-242 or 48, for example. Curium-248 is really the hot shit. Everybody wants that. And a small smidge of that is now turning into berkelium. Now we know that, yes, there are curium isotopes, but only the curium-249, which can't be deposited on some sort of disk, it can't be isolated to decay into berkelium. But again, we only have one isotope of curium. So depending on how you want to phrase it, yes, it's true, curium can decay into berkelium. However, if you look statistically at curium and do not prefer any isotopes, with that statement, most of the time you'd be wrong, because neither does the curium-242, 43, 44, 45, 46, 47, 48 do decay into Einsteinium, or, well, in our case, first of all, into berkelium. So this statement might have some truth. Yes, there is one isotope that can decay into berkelium. However, there are more isotopes that do not decay into berkelium in an atomic level. And again, it's the same thing here. Yeah, it brings a small quantity of californium. So we are talking about the berkelium-249. And again, here, I think it's purposely phrased very vaguely here. Quantum realm gods that roll, whatever they are talking. It's so unscientifically phrased in that case. But yes, there are californium isotopes that can decay leading to Einsteinium. However, it has to be a beta-minus emitter of californium. And again, the californium that is produced from the berkelium decay, so in our case, the californium-249, does not decay via beta-minus decay. It decays via alpha decay, not producing our Einsteinium. Again, yes, there are californium isotopes that could produce your Einsteinium. And in our case, that would be the californium-253, which would decay via beta-minus, producing Einsteinium-253, and not our 54 isotopes. Yes, californium-254 could also produce our Einsteinium, but again, it's another isotope. And coming from the berkelium decay produced californium-249, it's not something that could just happen just like that inside of this sample. So when starting with curium, you won't be able to have berkelium, which could decay into californium, but not in our case. And again, californium could decay, forming Einsteinium, but again, not in our case. These are all so vaguely phrased, and no scientific analytical data, I mean, if you're selling these for 3,000 euros, you should be able to afford that, is given, that I would just doubt. Sorry, but I don't think that anything past curium is really legitimate. And it's so frustrating because Luciteria does a really good job. I like sellers that sell elements to collect, to get people excited about chemistry or elements or nuclear chemistry in that case. And they could just pose at curium. They have a monopoly. I think they are the only seller that sells actual curium with some scientific proof that they have certain curium isotope. And they could just leave it at that and say, hey, we are the only seller worldwide that provides curium. You have curium. You can just pose at that. It's interesting enough. Berkelium, californium, Einsteinium just ruined your reputation because I think they are lying. If not, please correct me in the comments down below. And also, I know Luciteria does not produce them themselves. They are just reselling. But however, as a reseller, you should also know what you're reselling and not just put a fancy text on some unknown sample in my case. With that being said, thank you for your attention and goodbye.